Hamiltonians for the first time, but only a little bit. And then we'll talk about composing systems as promised in the previous class. So let me start with a daily analogy because this will be helpful for what I want to say next in terms of housekeeping. So do you know these people, usually a bit older people who have been cooking for a long time, and then you go to them and you ask them for a recipe for something that you just ate that they cooked that was delicious. So for me, this was my grandmother when I first started university. She would make these amazing soups and ratatouille and whatnot, and I'd ask her, how do you do this? And she'd tell me, so you cut the carrots and the potatoes and you boil them, and then you just wait for long enough, and then you blend them, and then you add the spices and you season it. And for her, this was a complete description of the recipe. And I had not cooked until then, and I was like, wait. You cut them how? You wait for how long? And what is this about seasoning? Like how much pepper and salt should I add? And the point being that people who have been doing this for long enough, for them, some things are just so natural that they assume that everybody knows this. So of course you know how to season a soup. And I think I'm guilty of doing the same. I'm like the grandmother of quantum mechanics. And I've been doing this for a long time. And sometimes I forget like what you know or what you don't know. So in particular, someone told me, and thanks very much for this, that they had not learned about the Fourier transform in this particular year of computer science. And so they couldn't solve one of the exercises. Okay, so it's very important that you tell me when I mention some terms that you don't know, or we use some tools that you're not familiar with. So in this case, what we'll do is that Nuri will give a short introduction to the Fourier transform in the exercise class. Okay, so you, and really, like every time you feel like you cannot solve an exercise for some reason, just let us know, because then we can recap on this. Good. So the second topic for housekeeping is YouTube. So as you know, I put the lectures on YouTube, and it's more of a matter of when than a matter of if. At some point, I might not be able to do the lecture in real time. So for example, my kid will get sick because winter is coming, and he'll be home here during the day, and therefore it's impossible to have him be quiet for 2 hours. So I'll not be able to give the lecture in real time. So what I'll do is I'll record in the evening, and I'll upload it to YouTube, and then it will be online in the morning. So when this happens, I'll let you know, and then you can either watch the stream in real time or just watch it at your own pace whenever you want. Good. Next topic is Moodle. So sorry about this. Some of the forums were not working, and now I think we fixed them. I think now you can ask questions directly there. So I hope this is working. I think someone already tested this. So again, if something doesn't work on Moodle, just write to us. Finally, someone told me that they couldn't read the bottom of my iPad. I think this should be a problem on their side, but if more of you cannot read this, so if more of you cannot read like the last thing down here, please let me know in the chat now, and then I'll just avoid writing there. Okay. In any case, when I later upload to YouTube, you should be able to see everything. Good. Someone else also asked me which chapters of the book are relevant. So far, only a little bit of chapter 3, although they do things in a bit different order, but it's nice for this. So they do there the bit of Hilbert space, states, and properties, and a bit of observables. Okay. But today for the Unitary Dynamics, we'll follow chapter 5. So B and M stands for Ben and Mike, which is Ben Schumacher and Michael Westmoreland. And you can access the book for free if you use the VPN connection to ETH, or otherwise access it through the ETH library website. Okay, so today we'll follow more or less chapter 5 of this. I think that's all for housekeeping. Okay, someone tells me that they can read it. So let's start with the Unitary Dynamics. Oh, something else, sorry. I realized that if all the videos are online, maybe I don't need to do a half-an-hour recap of the previous lecture. So I'll stop doing this now. Okay. Stefano, are you saying this for people on your side or for me?
I'm saying it for people on our side. So if you have like your mouse on the middle of the screen and you press Alt, then you have like full screen.
Okay, perfect. Okay, thanks so much.
Maybe this is the issue. I don't know.
Yeah. Okay, very good. So everyone just try this, and if you still have problems, just let us know. Great. Okay, so then let's start. So we were starting with unitary dynamics, which, as we saw, was the dynamics of a system that's evolving isolated from everything else for now. Okay, and what we saw was, sorry, a future state is given by the past state with some unitary acting on it. Okay, and what's a unitary? It is just a matrix that satisfies U times the adjoint, same as the adjoint times U, which is just the identity matrix. Okay, and now we're going to see some properties of this matrix first, and then we'll derive the Schrodinger equation. Okay, so properties. So the first thing is that it preserves the norm. Okay, so we assumed first that the norm of a vector, which is the inner product with itself, that is just 1. And now let's see what is the inner product of the evolved state with itself. Well, sorry, this. Right, so first of all, this thing here is just U, it's just the evolved state, and then I need to take the adjoint, which means I need to take the transpose conjugate. So in particular, of course, I get the U dagger there. Okay. Well, but this whole thing is associative, so I can put the brackets like this. And this we know by definition, this is just the identity, right? So then we have that the inner product is preserved by the unitary. Okay. This was the first product. And now we can ask, well, what happens to the product between two different states? Okay, so now we have a second state, phi, that also evolved under the same unitary. Okay. And now you can ask, well, what is the inner product of, say, phi prime with my other state psi prime? And this is going to be exactly the same again. So it's going to be, well, this state evolved. The other state is also just the evolution of psi. And this is check. This is just 1. So it doesn't change the inner product also between two states. Okay, when is this relevant? Well, when you know, for example, that this corresponds to some measurement, some measurement outcome, okay, and you want to say, well, now both my measurement device and the state that I was measuring, they both evolve in the same way. Does this change the probabilities of getting a certain outcome? And the results that this tells us is that no, it doesn't change it. Okay, it will also be useful much later for for telling us that it doesn't change how well we can distinguish states, having them evolve under the same unitary. Okay. So now we can look and try to see what the eigenvectors and eigenstates of the unitary are. So that's property number 3. Oh, let's be consistent. So let's assume that we can diagonalize the unitary, which we can, in some basis, such as some eigenbasis and some eigenstate. So this is just K. Okay, so this means that in this basis, it looks like this. Yeah. The matrix looks like this, and I want to know more about this U case. Okay. So how do we do this? Sorry. Give me a sec. Yeah, so we know that, well, this case must be normalized because there are some orthonormal bases. Okay, so K, there's some orthonormal bases, and now we can write this case as what I'm saying here is that, well, just because of our result before, if we evolve each K, it should not change the inner product, right? So you can add the U's here for free. Okay. Right, so now we know the result of this. So this is just applying the U. It's an eigenstate, so you just get here UK star because it was the conjugate. You get UK. Okay, right. Just get the eigenvalues, and now these are numbers, so we can bring them out of the brackets. So that's UK tac UK KK. Now this we know is 1. And then we're left with, I mean, this is just the modulus of UK. Good. So then we get that, well, the modulo of UK is 1, which means that UK must be a complex number of with some phase. So this means UK, but with amplitude 1. So we can write it as I and some alpha K. Okay, so this is alpha K. Which means we can rewrite our unitary as U sum over K, EI alpha K, KK. Okay. In its eigenbasis. And this is true of all unitaries, so all the eigenvalues have modulo 1, they're just phases. Okay, good. So now we're going to leave this aside a little bit, and now we're going to think about the dynamics. Okay, so we think about a system that changes in time. So such that some, well, let's say, sorry, some function, the state at some time t depends on the unitary, that depends on time and the initial time. Okay, and the initial state. Okay, and now we want to know a bit more about this kind of evolution. So let's think first of what's the time derivative. And so, by the way, when I mean time derivative, of a vector, what we mean by this? Well, we have the vector and we do just ddt of each of the coefficients, okay? This is what we mean. But we have another way of thinking of the time derivative, which is just ddt is just a limit when this delta goes to 0 of check of t plus delta minus the state t over this delta, right? Where delta is a small interval of time. So now we plug in what we know about the time evolution. So we have limit t goes to 0, and here we have this unitary, which is depends on t plus delta and initial time. So I have t minus psi of t, psi of t, over delta. And now here we can put here for free an identity matrix, right? And now we can pop the state out because it's the same state. So we have this limit when delta goes to 0 of u of t plus delta t minus the identity over delta, and here psi of t. Okay, now look, this is a matrix, this is a matrix, so overall this thing here is going to be a matrix, okay, of the same dimensions. So we just call this whole thing a matrix G. Okay, and now what we have is that a time derivative of the state depends linearly on the state itself, and the coefficient is given by this matrix G, okay, which will not be an important matrix, but let's try to find more about this thing. Okay, so again, we're going to use some of the properties we saw before of the unitary evolution. And so we know that the unitary evolution does not change the norm of the state, right? So we know that in particular, if the norm of the state is not changed, then the time derivative of the norm of the state must be 0. Okay. So it's a time derivative of this thing. Now we just so this is a derivative of some object A times some object B, which from basic calculus we know is given by this, right? The derivative of the first times the second plus the first times derivative of the second. So we go and do this. So this will be d dt of in brackets plus t times d dt of check right? And now we just replace this object here with what we saw before. So we just replace it with this operator, a known operator times the state. Okay. So this is check of T. And remember, because it's the conjugate transpose, the unchecked, you get G tech. This is the first term. And then, oh, and then we get the second term. G. And here comes G. Okay. So now, look, this is the same as this, and this is the same as this. So we just, everything is linear, we just put them outside. So we get G, and here we have G plus G psi of T. Okay, there we go. And now this must be true. So this, sorry, there's a plus here. So this notion, this equality must be true for any initial state, right? And this is some operator, let's call it operator A. Okay, so what's the thing that satisfies this being zero for all possible initial states that have norm one? Well, it needs to be zero itself, right? So let me just make this smaller. Put it here. So the conclusion is that G plus G equals 0. And this is a property of matrices, which we call being anti-Hermitian. Okay. But we don't like working with anti-Hermitian matrices. So instead, we're going to make G equals some I so this is just going to be a constant, which for historical reasons is the Planck constant, which has some units, which we'll look into much later. Okay, and now because I have the I there, then this operator gets to be Hermitian, which means that H, it's H plus. Okay, so it's the opposite of as before. So, and this is going to be what we call the Hamiltonian. And now this leaves us with the Schrodinger equation, which is, so now we come back here to this thing here, and we just rewrite it. Okay, and we get that by putting all the constants in the right place, doesn't matter so much, we get okay. So I think here it's even it's probably even I over H part there. Okay, and this is what is called the Schrodinger equation. Now, why did we go all the way to find a Hermitian operator instead of working directly with the G? That's because the Hermitian operators also correspond to observables. So in particular, they have real eigenvalues, and they can be seen as observables. And in particular, the operation H will correspond to the observable of energy for the system. Okay, but this is something that we will see in a bit, much later. But for now, it's just good to know, well, look, the dynamics of a system are given by this thing called the Schrodinger equation. And to get the unitary from here, if this H does not change over time, if the H does not change over time, then we get that the U of t is just E2 minus I over H bar H times some period times this period t. Okay. And we can put here even t minus t0. Okay. So this is something that we will see much later on. And we'll study properties of this Hamiltonian and properties of the Schrodinger equation, and we will see applications to real systems on the Thursday lesson. Okay. But for now, I think I want to leave this here, and we will instead now talk about how we compose different systems. Okay. And then we'll come back here later. Very good. So. Because sometimes we have not just one system, but in all physically relevant situations, we have more than one system that we want to evolve, and we want to think about how do we treat this mathematically. So let's see. Composing. Okay. So the idea is, so I have some system A, it could be a qubit, or it could be like the position of a particle, like we saw in the exercise class. And we have some system B here. And I want to talk about, for example, what happens when there's a joint evolution of the two. Or I want to talk about there's a joint evolution of the two, and then I measure just the first system or just the second system. How do I represent these things? Okay. And this is represented by the tensor product. Which is a mathematical object that's kind of designed to satisfy these properties. So I'll just write down the definition and what the properties are, and then we'll see some examples. So we have that. So let's say this is system A, so represented by the Hilbert space HA. And then we have the Hilbert space HB. And their tensor product is given just by the span of vectors in A. Tensor, again, we don't know what this means yet. Vectors in B. So the idea is that all this phi A belong to HA, and the psi B belong to HB. Okay, good. And satisfying, and what properties does it satisfy? Well, one is that operators will act linearly and independent. As satisfying this, UA. This means I apply some operation U on system A and some operation V in system B, And from now on, it's going to be important. Whenever it's not obvious from context, we always need a subscript to tell us which system this is. So this acts on some state, say A, tensor phi B as just evolution of the first tensor, the evolution of the second. So this means that the UA only acts on system A and BB only acts on system B. And we'll look at examples in a second of this. The second property is what is the inner product in this new space. And again, it acts linearly. I'll explain later what this means. To act linearly as what you'd expect. So if I have some psi pi on A, this is some phi on B, and I want to see what the inner product is of with some other states on A and B. Then this is just, we take the inner product of the first, and now this is a number, so this belongs in C. And the inner product of the second, and this also belongs in C, so the operation between them is just multiplying them. Okay, so it's just a simple multiplication of complex numbers. Okay. So these are the properties that are relevant for now. And let's just talk a little bit about notation. So, and this is, we don't always want to, especially when you talk about qubits and many, for example, if you have a quantum circuit, you have many qubits, you don't want to write the subscripts all the time. So sometimes we write, instead of some state, for example, state 0 in A, tensor state 0 in B, sometimes we just write 0A, 0B, so we forget here the tensor product symbol, which is the odd times. And sometimes when it's really clear that the zeros correspond to different systems, we can even just write it like this. And you know, and when which systems it is clear from context, sometimes we even write just this. So let's see. Let's see an example. And let's see the example first of just 2 qubits. Two qubits A and B, so the Hilbert space HA, tensor HB, so this was 2 complex numbers, right? Remember, this was also 2 complex numbers. And this is going to be equivalent to, I think, 4 complex numbers, so vectors with 4 elements. So let's see what the basis elements are. I'll just write them here. So 0, 0. This is, remember, 0 is this vector, tensor itself, and in matrix form. So don't worry about if you don't know how to work with the tensor product in matrix form, because most of the time we use only direct notation directly, and will not use matrices and multiply matrices by hand. Although we'll do it here to see some examples, but that's about it. So this is this. So this is one basis element. Okay. the 0, 1, which is 1, 0, tensor 0, 1. This is the second. One, 0. Again, same thing as here with a different order. It's going to be 0, 0, 1, 0. And finally, 1, 1 is going to correspond to the vector 0, 0, 0, 1. Okay. But now let's see how some operators act here. So first we're going to see what happens when we act with only one operator. Okay, so we'll take with only operator on one qubit. So we'll take first the kind of one qubit gate. So we'll take the initial state to be 0, 0. And we want to act with just the Hadamard on the first one. Okay, let's put here the subscripts for now. We want to act with the Hadamard on the first one. So how do we represent this in the big picture of saying 2 qubits? We'll say we do nothing on the second one. So we apply an identity operator on the second one. Okay. And now let's see how this acts. So HA tensor the identity on B, acting on the state 0, 0 on A and B. This is the same as having HA acting on 0 tensor, the identity acting on 0. Right? Systems A and B. Well, the Hadamard, if you remember from the previous lesson, the Hadamard acting on 0 gives us a state plus, which is 0 plus 1 square root of 2 tensor 0. Okay, so this is B. A. Yes, so I'll just recap here what the Hadamard was. It was 1, 1, 1, minus 1, square root of 2. And we saw that it mapped 0 to plus, for example. It mapped 1 to minus. Okay, so now we have this state. And this, everything is linear again. We can break it apart. So this corresponds to state 0 on A, tensor 0 on B, plus 0 on A, tensor 0 on B, over square root of 2. So now let's suppose we want to now apply some other gate here. So for example, let's apply the bit flip. Oh, sorry, I made a mistake. This should be 1 here. No, let's apply now the Z gate on this state. Okay, so now we want to apply the Z gate on the first qubit again, tensor the identity. Okay. And how do we represent the whole thing? Well, first we start with state 0, 0, then we apply this Hadamard A tensor identity in B. And now we apply this, right? So the most recent gates are on the left. If we want to represent this in the circuit form, we'll have 2 qubits here. And remember, time goes from left to right. And what we did was to apply here first Hadamard. And now we apply here a Z gate. And on the second qubit, we did nothing. Okay. So let's see how this happened. So we take Z on A, tensor the identity on B, And we apply to this state, so 0. I will let go of the subscripts for now. You know that the first is A and the second is B. Okay, square root of 2. And now remember what I said before about it acting linearly, right? So that's operators act linearly and independently up to this, which means that if we have a sum here of so let me do it like this. If we have here a sum over I of some operators ui vi, then what we get at the end is a sum over I. Yeah, so they act nice and linearly. And also if we have some coefficients here, we get the same coefficients there. Okay. So, and the same happens if here you have, okay, let's make this more complicated. So if here I have a sum over J of some vectors J, then we'll get here the sum over J, and why not, let's put some coefficients, Bj. We get the coefficients here, Bj. And what I want to do is the equal sign. And J, J. Okay, so everything acts nice and linear. So here we are. So this is just going to be nothing happens on the second qubit, so it's going to be Z applied to 0 on the first, check, plus Z applied to 1, again the first qubit, tensor the second one, okay? So I can put here again the subscripts for now. Okay, there you go. This whole thing multiplied by 1 over square root of 2, and now let's take them to the next page. Copy. Paste. Okay. So what was this Z matrix? If you remember, so Z was this matrix, which could be written as we saw last time as 0, 0, minus 1, 1, minus 1, 1, okay. Which means that when it acts on state 0, it does nothing to it, as we saw before, so this gives state 0, 1a, 0, plus, and here when acts on 1, it gives it a phase of minus 1, times 1, 1a, 0, 1b, the whole thing over square root of 2. So this whole thing is now what? So it's going to be 0, a, 0, and b minus 1, a, 0, 1b over square root of 2, which we can still factorize the second system out because it's the same, right? It's the same here and here. So we can write it like this. 0 minus 1 on system A over square root of 2 tensor 0 on B. Okay. And sometimes we put the tensor product, which is just the state minus on A tensor 0 on B. Okay, so this is the easy one, and now let's make a 15-minute break. And when we come back, we'll see a gate that actually correlates the two systems. Okay. So I will see you at 10:45. And I will stop the video, but I'm still here. So if you have any questions, you can ask now. Okay. Okay, can you see my screen? Stop being able to see it. No screen. Oh, there you are. Okay. Yeah. Okay. Got it. So we continue. So far we only saw how to implement a gate that acts only on one qubit, but we saw how the effect on the global state. But now we will act with a gate that is actually acting on both qubits, on both systems. Okay, and remember, qubits is just an example. So this is one of the most important gates, both in quantum information, but also in quantum physics in general and quantum computing. So this will be, let's look at 2-qubit gates, and we talk about the control NOT gate. So if you're a computer scientist, you know what a control NOT is. And that's a gate that looks at the first bit, and the first bit is 0, does nothing. But if the first bit is 1, then it flips the second bit. Okay, so this is going to be exactly the same. So the CNOT, I'll write it first in Dirac notation. So it looks at the first bit, at the first qubit, and if it's 0, okay, then it does nothing on the second. But if the first one is a 1, then it flips the second. And as we saw last time, the bit flip operation corresponds to this matrix X, the Pauli X matrix, which is, it's 0, 1, 1, 0, which corresponds to 0, 1 plus 1, 0, right? So if it sees a 1, it transforms it to a 0. If it sees a 0, it transforms it to a 1. Okay. And what's interesting is not how it acts on states that are in the computational basis, but how it acts on states that are on other bases. So it also has a matrix form, and it's a 4x4 matrix, right? Because it acts on this 4x4 states, and it looks like this. And one way of trying to look at matrices and try to infer the Dirac notation, which is what's easiest to work with, is like the columns correspond to column vectors. So this corresponds to the component 0, 0. This corresponds to 0, 1. This column corresponds to 1, 0. And this column corresponds to 1, 1. And these rows correspond to the brush, 0, 0, 0, 1, 1, 0, and 1, 1. Okay. And we can also write it in its full glory. So we just expand the Dirac notation above. So if it's 0, no, let's not do this. But it would be 0, 0 tensor. The identity is what? Is 0 plus 1 plus 1, 1 tensor. And here you have this X gate, which is 0, 1 plus 1, 0. Okay. And now you can expand this whole thing and you get the 4 terms. Let's not write them down here. How do you represent this in circuit notation? So this gate is represented by, there's a 2 qubits, and the control gate is very much like the classical one. It's represented like this, where this one we call the target, and this one we call the control. Okay, so let's see how it acts. So this is across here. Right. So let's see how it acts now on our states, and let me make less of a mess here. There we go. Okay. So let's see how it acts on our state. So what did we have before? We had applied the Hadamard and the Z. And now let's apply also the CNOT. In fact, let me copy all of this. So we had that, and now we want to apply here the CNOT, which corresponds here to the circuit representation to doing this. Okay. So we had our state, which was this state here. Let's copy it. I like this a lot. And now let's copy here our gate. And let's put this gate. This is amazing. I can change the color of the gate. I can take this and resize it. There we go. Okay. So we just expand the state. Okay, everything acts linearly. So how do we do this? Let's take first the first component. I'll write it by hand. 0, 0, tensor the identity. I'll omit the subscripts for now. And we take the first component here. So we take this together with that. So we have 0 acting on 0, 0 plus 0, 0 tensor the identity acting on this component. And it's not a plus, it's a minus. Now plus the second component here. So we have 1, 1 tensor the identity acting on 0, 0 minus 1, 1. Sorry, not tensor the identity. Tensor x and b 1, 1 tensor x acting on 1, 0. Okay. You know, each of them we already know that, you know, this will act on this and this will act on there. Okay, so I'll not do it explicitly. So what we have here, 0 acting on 0 does nothing. And here the identity acting on 0 does nothing. So here we have 0 stays and 0 stays. Minus, now we have this acting here, which I'll just write it here. So 0, 0, 1 tensor the identity on 0. Okay, this is system 1, this is system B. But we know that this is a number and this number is 0 because these vectors are orthogonal, right? So this part here, this is 0. So the whole thing is 0. So minus 0 plus, here the same thing happens on the other side. So this 1 kills out the 0 there, so we get 0. And now minus, and now comes interesting. 1, so we have 1 acting on 1, so you get 1. In the x here acts on 0, and as you saw before, it flips it to a 1. Okay, let's look AB, AB, and everything is of course over square root of 2 over square root of 2, so we're left with the state 0, 0, minus 1, 1 over square root of 2. And now something interesting happens, because before we had a state that also had more than one component, right? So this state here, or better seen here, right? It had 2 components, but we could always write it as a tensor product of some state on system A and some state on system B. This one here, you cannot do this. Okay, I will not prove this now, but I don't think we'll later see this, but believe me for now that you cannot write this state as a product of something on A and something on B. And this is what we call an entangled state. Okay, it's as simple as that. So, global states, some psi AB. So if psi on AB can be written as some letter on A tensor state of B, then this is called a product state. Meaning I have 2 independent states on system A and system B, and I just have the tensor product of them, right? Just means I have a global vision of these 2 local states. But if this is not the case, if we cannot write it like this, we say it's an entangled state. And for now, we leave it at this. Later on, we'll see that there's many ways in which you can decompose a bigger system into small subsystems, and the notion of entangled is relative to this decomposition. But for now, forget it. We start with 2 small systems. We start with 2 independent states, 0, 0. We apply some gates, and now we have a state that is no longer product. It's what is called an entangled state. Okay, so example are these states that are like, for example, 0, 0 plus 1, 1 over square root of 2, or the ones that we saw now, which was having a minus here instead of a plus. Okay. Good. And these states turn out to be very important for lots of tasks in quantum computing, in quantum information, which we'll see some of later on. They also are important in physics. So essentially, every measurement is a version of a CNOT gate. Every measurement, when you look at how it's implemented in reality, it's going to be taking 2 systems and entangling them together via something like this. So, but this we'll see much later on. For now, let's see what happens now if we want to measure a state, a global state, but we want to make a measurement just on one subsystem. Okay. So, and remember that for single systems, we had this rule. So we had the measurement being represented like a set of projectors. And remember that the probability of getting some outcome, let's call it X, let's call it I, on some state psi, was given by phi projector I, phi, right? And that the final state, the post-measurement state, was pi I phi over this probability, over square root of this probability. Over this probability, sorry. Okay, good. So now what happens if we have two systems? So we have, for example, in the example we saw before, let's copy it again. Not with the bracket. So now we have these two systems, and now we want to measure just the first. Okay, we want to make a measurement here of just the first qubit A, and we want to know what's the probabilities of getting some outcomes and what's the final state. Okay. And the rule is going to be very similar. So now we have a measurement in system A, and it's going to be represented by projectors on A. Let's put the index there. And what happens on system B? It's nothing, so we represent this by an identity matrix. Okay. An identity matrix on B. Matrix on B, so that the probability of getting outcome A when measuring some state psi AB, it's going to be psi AB, and now comes the projector in A. So tensor the identity on B, and the joint state psi AB. And the post-measurement state is going to be pi A tensor the identity on B psi AB over the probability. Okay, so let's see an example to see what this means in practice. So we have our state, which is, what was it? Here it is. So we have psi AB. What's this? And we want to measure in the Z basis in the first qubit. Measure A in Z basis. Okay, this means that the projectors are, as we saw before, so remember that Z was 0, 0, minus 1, 1. These are the two projectors, so we have the projectors 0, 0, and now here the identity on the second, and the second one is going to be 1, 1. The identity on the second. Okay. A, there we go. Okay, so now we take this and we apply this to the state, right? So what's the probability of getting outcome 0 on this stage? So we take this whole thing. So let's say psi AB, and now the projector for 0 is this first one, so we put here 0, 0, tensor the identity psi AB. Okay, and this is going to be, now we plug in the state, so we have 0, 0, 0, minus 1, 1, over square root of 2. Here comes 0, 0, tensor the identity. And now here comes the state again. There goes the state again, right? And let's check this. Put it up there. Everything up. There we go. Okay. So now it's going to be again the same thing. So this acts here. And let's see. We have many terms. So let's do one at a time. So we have 0 on A. I'll write all the stuff. Then we have this 0, 0. That's this operator. And then we have 0 on B. Okay, so this corresponds to this first term and this. And now we sandwich it with this on the other side. So that would be times this whole thing. And then we have 0 in A, 0 in B. Okay. Over 2. Plus 4 other terms, plus 3 other terms like this. Okay. But let's just look at what happens on this one term. And that's so this is 1, right? This is 1. And now on the what's left here is this vector being multiplied by this vector and that vector being multiplied by that vector. So that's so we have the 0, 0, that's the first one. Then we have 0, 0 from the second one. I'll leave the subscripts here so you know where it's coming from. 0, 0, check. Where's square root of 2? And this is 1 times 1 times 1, so this is 1 over 2. Yes? Okay. Now we'll do it to the other terms, but turns out that the other terms, they'll all be 0 because one of this, if we look at all the other terms, so in this one we have 1, 1 here, which is immediately killed by this, so we get 0. The second, then we have the term that is this, and it also has 1, 1 and gets killed there. And then we have the term that is 1, 1 and 1, 1, that's even overkill, they both die. Okay. So overall, this is the only term that survives. And the term that survives is, it's 1 over 2, which gives us the probabilities. And now if you look at so we leave this, if it was a bit fast, you can try to do it again at home. But let's look just at what the post-measurement state is of this. Okay. So say we measured it and we obtain outcome 0. What's the post-measurement state? So this was 0, 0 times the identity acting on the state 1 over the probability, or square root of the probability, we'll see in a moment. So here we had 0, 0. Yes, square root of the probability. And you don't want this notation yet, so 0, 0 minus 1, 1. Yeah, so that is square root of the probability, and here it's also square root of the probability. Good. And here it's also square root. Good. Good. So this gives us square root of 2. And now, again, we look at what terms survive of the sum, and we have the 0, 0 acting on state 0, tensor the identity acting on state 0 on B, say this is B, minus 0, 0 acting on 1, tensor the identity acting on 1, second one, over square root of 2. So now again, this is a number, that number is 1, and this is a number, and that number is 0. So we get state 0, and what survives here is just this is in A, and this is a 0 in B. Okay. Which means what? And here nothing survives, right, of that term. So we started with a state with we started with this state. We start with this state on both systems. Then we measure this first system, and if we get outcome 0, which happens with probability 1/2, then from our perspective, our updated state, post-measurement state, is now 0, 0. Okay, so also on the B system, it's 0, which means that if now we want to measure the second system, so now let's say we want to measure B in a Z basis again, what's the probability of getting 0? Well, now we have the state 0, 0. And now we have what's our operator? Now it's the identity on A and the projector over B. Okay. And this is just 0, identity on A, 0. That's a number, and the other number is going to be this here, 0 on B, this operator, 0 on B. Okay, let me do something nice for you. Check. The whole thing here. Check. And this is also light blue. Okay. So now we have 3 numbers here, and they all are 1, right? So this is the same as 0, 0. That's 1. This is 1. This is 1. Okay. Which means we measure it. We measure the first qubit. We got outcome 0. And we know now, without even measuring the second one, that if we were to measure it in the same basis, we'd get outcome 0 with certainty. But to start off, the probability of this happening was 0, 0. We can also represent this global, so these 2 measurements. So now what we did was, where's our circuit? Let me get the circuit. So what we did now was, let's prolong this line here. We measure the first one, and then we measure the second one also in the Z basis. Okay, Z, Z. And if here the outcome, we use double line for classical outcomes, was 0, then this one is 0 for sure. Okay. We could have done it the other way around. We could also have done it the measurement at the same time. We could represent a joint measurement by just the operators. So if we wanted to do just a joint measurement in basis Z tensor Z, then we just represent it by the operators. So 0, 0, tensor 0, 0. This corresponds to outcome 0 and 0. or 0, 0 tensor 1, 1. This corresponds to outcome 0 on the first qubit and 1 on the second. 1, 1 tensor 0, 0. And let me just represent it like this because I'm running out of space, which should not be a problem at all. Let's see. Oop. There we go. 1, 1 tensor 1, 1. Okay. And if you look at the probabilities of this for this stage, the probabilities will turn out to be exactly 1/2 for this, 0 for that, 0 for that, and 1/2 for this. Which means if we had measured the first qubit in Z basis originally and we had gotten outcome 1, then the post-measurement state would have been, instead of being 0, 0, it would have been 1, 1. And then we'd know that if you measure the second one here, you'd get a 1 as well. Okay? So we have, with 50% chance to get 0, 0, and with 50% chance to get 1, 1. And it doesn't matter in what order we make the measurements. We could even like send these measurements to space, put them very far apart such that they're space-like separated, which means that there's no before and after for them, and measure the two, and we still get with 50% probability 0, 0 and with 50% probability 1, 1, which means that the outcomes are always correlated. Okay. And funnily enough, this correlation happens not only if you measure in the X basis, but also if you measure in the Z basis. Not only if you measure in the Z basis, but also if you measure in other bases. So we'll see this in the future exercise sheet, I think not this week. Meaning that the outcomes are always correlated for these entangled states. Okay, in fact, it doesn't matter in which basis you measure. There'll always be a correlation between the two outcomes. And this is what Einstein, Roosevelt called, not Roosevelt, sorry, called spooky action at a distance. This idea that, oh, if I measure and I get outcome 0 here, then I know that on the other side, there will be an outcome 0 as well. And this is something that is not that spooky. We'll see later why not. Or we'll see it also in quantum information theory, but it's something that's very useful for many tasks in quantum computing and in quantum cryptography, for example. Okay. So that's measurement in joint measurements. Note that not all measurements need to have this product form. So now we can have global measurements on both qubits if you have access to both at the same time, where the projectors are global projectors and they're not necessarily in this nice tensor form. Good. We will only see now one example where we don't have just qubits. But let's say we have a qubit and then a system that is, we could do a continuous one, but let's do a discrete one. So let's imagine now that we have a little particle, okay, an electron, say, which inside it has 1 degree of freedom. Normally people say things like the spin of the electron, okay, which we don't need to know for now. We'll look later at what the spin is, but for now we just say this is represented by a qubit. Okay, so we have C2. And then this thing also has a position in space, okay, which we'll represent by a discrete Hilbert space for now. Later on, we'll see the continuous case, and you'll see it also in the exercise class, not this week, but next week. Okay, so we'll have that HA tensor HB is a span of 0 n, and one n belongs, for example, to z. Okay. So meaning that the position can be, for now, it's not a real position, it's just some Hilbert space, which we call the position, which has discrete steps. Okay, and inside the spin, there's a 0 and the 1. And now we're going to look at a gate that acts a little bit like the CNOT gate that we saw before. Okay, so let's look at the gate. And we wanted to do the following. We wanted to do 0 on A. If this is 0, then it does nothing on B. Or actually, let's let it do something different, but not nothing. You're going to go up. And if it's 1, it's going to go down. Yeah. Where up is going to take some state n and is going to output n plus L with sum over n. And down does the opposite. Okay, so we take n and the output n minus L. Okay. And why am I doing this? So now we look at a very, very, very simplified model of something called the Stern-Gerlach experiment. Very, very, very simplified, okay? Later on, we'll see the actual experiment. But the idea is that you have some particle that has an internal degree of freedom, in this case it's a spin, and the spin turns out to respond to a magnetic field. So here comes the spin, here comes the particle, and here at some point we apply, there's some object here that applies a Hamiltonian that implements the rotation, and the rotation is going to be something like this in practice. Okay, it will not be exactly that. Which means the following, that if the particle, so let's see, this is x in this direction, that if the particle had spin 0, or if the spin was in this state 0, then it's going to go up, and if it's 1, it's going to go down. Okay, and then at the end of the day, what people do is they don't measure the spin directly, but they measure the position of the particle by letting it hit some screen. Okay, it hits some screen, it excites some electrons there, it releases some photons. Okay, so then if it hits here, then we can see that it did. Okay. So let's just see for now what happens to the state of the particle, and it's exactly the same. Okay, so the idea of this exercise is, one, to show you a first approach to the Stern-Gerlach experiment, and to just see that we can apply this kind of gates that act like the CNOT, in the sense that they entangled the two systems, and we can apply them to systems that are not just qubits. Okay, so when we act with U, and let's suppose that the initial state was some psi on the spin, spin is A, tensor, say it was in a very nice position, it was in position 0. Okay, it's never going to be like this, and next week we'll see a real life version of this. Is going to be like a constant function. And the psi A, we don't know what it is, right? So it could be some alpha 0 plus beta 1. And just because you might see this notation elsewhere, sometimes we say that 0, physicists write this a lot, so this is an arrow pointing up, and 1 is an arrow pointing down. We just say the spin is up or the spin is down. Okay? It's the same as in the Bloch sphere. Remember, this was 0 up here and 1 was down there. and this is x, the 0 corresponds to the position. Okay. So we have u applied to this stage. So then what happens is that we get, well, we get alpha. And now what happens when this whole thing is applied to 0 on A? Well, then this term dies, and then only this term survives. So we get alpha 0 on A. And now this term, well, I'll just write this. So check, acting on 0 on B, plus beta. And now it's the same thing. So if I apply on here, this term is going to die, and this term survives. So 1 on A, and delta 0, delta down 0, okay. 1B. So you get, so now what is this delta? Well, it acts with all the ends possible on here, so only the term 0 survives, right? But I'll do it sum over n plus L, n, and these all act on 0, okay? Plus beta 1, and now the same thing. Except that here it is n minus L, and here is a 1. So this gives us what? Which I can do. Check, oops. Yep. So the only things that survive here is when n equals 0, so you get 0A, and here you get L being some large number corresponding kind of to this distance here, plus L minus L, plus beta 1, and here you have the state minus L on B, on the position, right? So in the case where alpha was 1 and beta was 0, okay, if alpha equals 1, then we don't have this term here, which means that the particle will end up here, L. So when we measure it, we know for sure that the spin was up before. Okay, this is a way to measure the spin without measuring the spin directly, but instead measure the position. And if beta was 1 and this part doesn't exist, then for sure we know that it is down there. Okay. If it was a superposition of the two, so both alpha and beta are non-zero, then when we measure at the end, with the probability alpha square, we'll measure L, and with probability beta modulo square, we measure minus L. Okay. And if you do this many times for the same initial state, then we can work out not the exact amplitudes, but this alpha and beta, and have some idea about the initial spin. Okay. So later on, we'll see first how to replace this discrete system here with a continuous variable. We'll see how to replace this this interaction that here is really a very tight interaction, it just means shift by L, with what's really happening, the real dynamics of this. And for this, we'll use the Schrodinger equation that we introduced in the first part of the lecture. And then you'll be able to actually replicate the whole experiment. This kind of interactions will also be useful later on when we study heat engines and thermodynamics of quantum systems, the kind of engines that we design use again this kind of CNOT-like entangling operations. Okay. That is all for today. On Thursday, I think we'll continue with the Schrodinger equation and see how different physical variables evolve in time and see what the role of the commutator is, etc. So that's all. I'll see you on Thursday, and in the meantime, I can answer questions if you have some. And go to the exercise class. It's also on YouTube, but you can answer questions. You can ask questions in real time if you attend the class on Zoom.